So let's start with the first topic, which is model of the atom. And the model of the atom may come in the exam from year to year. It's not in every single exam. What you need to know about this is the comparison between the three models, the Brown pudding model for J.J. Thomson, Rutherford, the nuclear model for Rutherford, and the Bohr model for the electron shell model. So Brown pudding model, J.J. Thomson discovered the electrons, and he described the atom as positively charged balls with negative electrons embedded in it. Rutherford later on discovered the nucleus and that the nucleus has a positive charge. When he did his experiment with the foil, gold foil, he discovered that the mass of the atom is centered at the center, and that the nucleus is positively charged and the electrons just surround the positively charged nucleus. He didn't speak about energy levels. Bohr is the one who discovered the energy level with his model, which is the electron shell model. So he described the electrons as existing in shells or orbitals of a fixed energy, and that when the electrons move between the shells, an electromagnetic radiation is emitted or absorbed. Later, he discovered that not all the electrons within the same shell have the same energy. This is why he discovered as well the subshells, as we know now as the S, P, D, and F. Sometimes in the exam, they may ask you to write the electronic configuration of a certain element or for an ion. You don't need to even look at the atomic number. You just need to locate its position in the periodic table and use the periodic table to write the electronic configuration. So the first two blocks here are the S block. And this one on the right here, these six from 3 to 0, these are the P blocks, which means the outer shell electrons in the P suborbital, and the S means the outer shell electron in the S suborbital. And then the one in the middle here, these are the D blocks, or as we call them, the transition metals. So when you try to write the electronic configuration, you just need to locate where is the atom. For example, if I'm going to attempt the zinc here, we can see that the 1s is completely full, and then we have the 2s, the 2p, then the 3s, 3p, then the 4s, which is filled before the 3d. Remember that 3d has higher energy than the 4s, so that 4s is filled first. And then for zinc, it will be 4s2, and then at the end, it will be the 3d10. So this is how we write it rather than trying to do the calculations. The electronic configuration, there are some exceptions with this rule I was talking about. Because we have copper and chromium, there are some exceptions for filling the subshells where there is stability associated with a half-filled or fully filled subshell, especially when we're talking about the d orbital. So an electron shifts from the 4s into the 3d subshell to achieve this stability. If so we have for copper, the expected electronic configuration would be R1 and then 4s2 and then 3d9. So we said that the 4s will be filled before the 3d because the 3d has higher energy or the 4s has lower energy. But actually what happens is that one electron moves from the 4s into the 3d because now we achieve a full sub orbital or a full d subshell. So this gives more stability to the copper. So when they ask you about the electronic configuration of the copper, you have to put it as 4s1 3d10. Also, chromium is the same situation, but now we will move the electron from the 4s to the 3d to achieve a half full d suborbital. So the expected one for chromium is 4s2 and 3d4. So, but the actual one is 4s1 and 5d and 3d5. So there are half filled the of the d subshell. This is why it's more stable. When we talk about the cations or the ions, when we lose electrons, sometimes as well, they ask you to write the electronic configuration of an ion. When we are dealing with the transition metals, where the outer shell electrons are in the d sub orbital, then we need to take note that although the 4s or the s orbital is filled before the d orbital, but they lose the electron first as well. meaning that for transition metal, for example, if we talk about copper as we've seen it, so for the ion from copper, it will lose the electron from the 4s before it starts losing the electron from the 3d. So this is only exception for the transition metals because the 4s will lose the electrons first, even though it has lower energy. Moving on to the ionization energy. What you need to know about the ionization energy. So most of the talk about ionization energy in the question comes in the form of describing the trend in the ionization energy. Sometimes as well, they may ask you to write the equation for the first or second or multiple ionization energy for a particular element. So remember that the first ionization energy is the energy needed to remove one electron from each atom in 1 mole of gaseous atoms, if they ask you for the definition, to give 1 mole of gaseous 1 plus ion. So when you write the equation, the thing that you need to take note of is that you need to add the gas symbol for both the atom and the ion, and you need to add the electron as well. Refer to only 1 mole of the substance when you do this as well. So successive ionization energy, the second, third, or whatever. Remember when you write the equation, for example, if we write the equation for the second ionization energy of sodium, we start with the sodium ion. We don't start with the sodium metal. And then again, we put it in the gaseous state, and then that will give us sodium 2 plus. This is the second ionization energy, also as gas, and the electron. Different factors affecting the ionization energy because they may ask you about the trend in the ionization energy, why it increases or decreases across a period or along the group. So there are three factors that affect the ionization energy: the nuclear charge, distance from nucleus, and shielding. Nuclear charge means that the nucleus has more protons. So as the atomic number increases, the number of protons increases, and the attraction between the outer shell electrons and the positively charged nucleus will be more, meaning the outer shell electrons will need more energy to be removed. So the ionization energy will increase across a period when because there is an increase in the nuclear charge. And then we have the distance from the nucleus. As you go down a group, you're going to see that the distance from the nucleus increases. This is because there are more electron shells now. So even though the nuclear charge increases, but the outer shell electrons become further away from the nucleus. So as the distance from the nucleus increases, the outer shell electrons will be less attracted to the nucleus, and the less energy will be needed to remove the electrons. And then shielding. So we can see the shielding in the also in the along the groups. So as you go down the group, there will be more inner electron shells, and these inner electron shells will act as a shield. So they shield the outer shell electrons from the effect of the positive nucleus. So as you go down the group, the ionization energy decreases, and this is because there are more shielding. So these inner shells, electron shells, will shield the outer shell electrons, so they are from the nucleus, so they are easier to remove. Electronic shell structure and ionization energy. So you can see that when we talk about the successive ionization energy for a certain atom or a certain element, you can see that the successive ionization energy increases. This is because you keep removing an electron from an increasingly positively charged ion. Also, there will be a jump in the ionization energy between shells. So as you go down, or as you go through the successive ionization energy, when you jump from one shell to another, there will be a jump in the ionization energy as well, because now we are removing electrons from a shell that is closer to the nucleus. Trends in the first ionization energy, we said that we have all the three factors: the nuclear charge, distance from nucleus, and shielding. So we talked about the ionization energy down the group. So we have group 2 elements or alkaline earth elements. One of the trends is the decrease in the ionization energy down the group. This is because of the increase in the shielding and the distance from the nucleus. And then the across the period, so the period will across the same period, you will have the same number of shells, electron shells, particles. So the shielding and the distance from the nucleus is not doesn't don't make massive impact here. The main impact will be the nuclear charge. As you go across the period, the nuclear charge increases, so the outer shell electrons will be more attracted to the nucleus, so will need higher ionization energy to remove or higher energy to remove. However, across the period, we have two exceptions. The two exceptions are the drop that you can see between group 2 and group 3. This drop is because in group 3, you start to remove electrons from the p subshell. So now the p subshell is further away from the nucleus and a little bit more shielded than the s. So when we are talking about period 3, though we are talking about 3s and 3p. So this is why aluminium will have the first ionization energy will be lower than magnesium. And we have another drop here between group 5 and 6, and the reason behind that is due to electron repulsion. So we have the phosphorus and sulfur. Phosphorus is group 5. They both have the same shielding, but phosphorus is group 5, where the electron that is removed from a singly occupied orbital. But when we talk about the sulfur, the electron is removed from an orbital that has two electrons. So there is some repulsion between these two electrons, which lowers the ionization energy needed to remove that electron. This is why there is a small drop here. Some of these definitions may come in your exams, so make sure that you know these definitions about the atomic mass, because we are going to talk about the mass spectrometry. And mass spectrometry is one of the typical questions in paper one. So sometimes in the question about the mass spectrometry, they ask you to define a relative atomic mass or relative formula mass. Remember that when you define the relative atomic mass or relative formula mass, you will always refer to the scale where an atom of carbon-12 is 12. So relative atomic mass is the average mass of an atom of an element on a scale where an atom of carbon-12 is 12. And when we talk about the relative molecular mass or relative formula mass, it will be the average masses of all of the atom in the formula on a scale where an atom of carbon-12 is 12. So the mass of carbon-12 has a scale of 12. Now moving on to talk about the mass spectrometry or the mass spectrometer, where it's kind of a typical question in paper one. The mass spectrometer or mass spectrometry has four different stages. The most important stage that we would need to talk about, which comes in the exam, are the ionization stage and also the detection at the end. So we have four stages. We have the ionization, detection, ion drift, and acceleration, drift, and detection. So, first of all, the different particles, whether they are atoms or molecules, get ionized in the first stage. They form positively charged ions, and then they get accelerated, and they all have the same kinetic energy. So, we know that the kinetic energy will equal half mv squared, where m is the mass of the particle, and v squared is the speed squared. So, because they all have the same kinetic energy, the ones which have lower mass will have higher speed. So this is why the atoms or the particles with the lower mass will reach the detector first, because they're going to have a higher speed. So let's start to talk about the two different types of ionization based on what you need for the exam. So we have two types, the electrospray ionization and electron impact. Electrospray ionization, when you dissolve your sample and then you push it through a nozzle at high pressure, and then you apply a high voltage. It's very important to refer to the high application of the high voltage. What happens when you apply the high voltage? Each particle will gain a proton or hydrogen ion. Now the ions or the ionized particles will have hydrogen plus. So if you have something like M, it will be M hydrogen plus, not M plus. And then the sample will turn into a gas made up of positive ions. So these positive ion will have hydrogen plus or will have a proton. The electron impact, on the other hand, the sample is going to be vaporized first, and then an electron gun will be used to fire high energy electrons at the different particles. This will knock one of the electrons off each particle. So the particles will lose one electron and they will gain a positive charge now. The second stage is the acceleration, where they are accelerated and they all have the same kinetic energy. They don't usually ask about that in the exam. The ion drift, as I mentioned before, it's because they have all have the same kinetic energy. The one with the lower mass will reach the detector first. And then the detection, what you need to know about the detection. So the ions are going to hit the detector, and each ion will gain an electron, generating a current, and the abundance of each particle is proportional to the size of the current. This is how we find the abundance of the different particles or different ions in the mass spectrometer. So the mass spectrum that is generated will give you the mass over charge. The charge is usually, most of the time, is +1. So mass over charge is basically the mass of the particle. The particle could be an atom and it could be a compound as well, and or could be a molecule. And then on the y-axis, we have the relative abundance. And then in case of electron impact, the ions that we detect, the m over z, will be the mass of that particular ion. But if we use the electrospray, the m over z will be the mass +1 because we added a hydrogen ion now. This is very important when we calculate the mass of the particles, or when we calculate the relative atomic mass or the mass of the isotope, when they ask us to do this, or the mass of the particle. So this is a typical question again in the question. This is a question where they give you the equation for the kinetic energy. And then they either give you the distance traveled and the time took by a particular particle, and then they ask you to calculate the mass of that particular particle. So how to answer these type of question? Remember that the mass that you use in the equation is in kilogram. It's not in gram. So if you're going to find the mass, remember that the value you're going to get is in kilogram. The speed, which is the v, it's in meter over second. Sometimes they give you the distance in centimeters, so you have to change that into a meter. And then when you calculate the value of the m, it's going to be in kilogram. You have to change this into a gram first by dividing by 1,000. So when you divide the kilogram by 1,000, that you're going to give you the mass in gram. This is the mass of one particle. Then they give you the Avogadro constant. So now you need to calculate the mass of 1 mole of that substance. The mass of 1 mole is basically the mass of the particle, whether it's an atomic mass or molecular mass. So the mass of one particle, multiply the mass of one particle by the Avogadro constant, that will give you the AR or the MR. So depending on whether it's actually an atom or is it a compound. Remember, if we use the electrospray, then the MR, the AR that you get, or the MR that you get, is actually not the MR or the AR, it's the AR +1. So to find the mass of that particular particle, you have to take away 1 because we added a proton. So the mass we calculated at the end is m +1, not the m plus. So this is very important. One of the typical questions as well, that they give you, ask you to give the equation, including the state sample for the formation of this ion strontium plus from strontium atom by